sorry. Okay, here it is. I'm not very good at looking at the chat, so I need somebody, a volunteer, who will tell me when there's a chat question and say it with voice. I mean, if you ask me by chat, it's likely that I will see it much later.
Sure, I can do that.
Okay, sounds good. And the other thing is, and this is, I would like, you know, let's try to do this as interactive as we can. Sorry, I'm trying to put the windows that, you know, I'm trying to place the windows in certain place, and Zoom is always putting them where they want. So feel free to ask and stop. This is supposed to be understandable. So if it's not, it's my fault, and feel free to ask me then. And this is a little bit, I mean, well, a lot of words to just say what I want to talk about. And there's two things I want to talk. It's the idea of dimension in mathematics, and, you know, what are regular polytopes? Well, maybe you don't know that word, but hopefully you will at the end of the class. And there's, you know, things on the side. So, and let me just see. So here I have a question, just to check. You can answer. You can. This is you can respond using a web browser or a phone. Oh, sorry. I have many windows. And is it as it active? Sorry, I'm being very clumsy.
I can send the link.
Well, no, people should be able to see it. Let me see. No, but it's not activated. Okay, I was checking my setting, but it was supposed to be working. I have an extra window that I don't know what it's doing. Okay, maybe here. Can you? Is this active? Yeah, it is. It should be. And I should be able. We should be able to see your questions if you're answering. Space-time. Okay. Length, width, time again. Can you see the answers?
No.
No. Okay, let me just should be able to see them, but I'll check here in my other computer. Oh, you're supposed to. Oh, so this is okay. Linear independence. Hi, Professor. Okay, partial vision, relativity, tesseract, quaternion. Okay. I'm going to change my setting because I was trying to work with Zoom and a window, but I think I have to use my iPad. So apologies for that. Well, there's 7 people who answered, as you see, 8. Let me see. Let me change my setting. I'm going to stop sharing and share something else. Okay. I still have 2 windows, which is very disturbing. Now you see this. Okay. Well, let me continue. Sorry, the technology is not helping today. So let's talk a little bit about dimensions. So what is the idea of dimension? So here, this is a very rough count. You know, we have a monkey and a banana, and the monkey can walk. And the question is, how many steps can the monkey do to get to the banana? And you can just, I'm sure you can guess, you know, if you look at it, it's approximately 2. The length of the step is approximately there. So there he is. If the banana is on the other wall and it's only 1 step, he can do that. If the banana is in the middle of the room, well, you know, he can do the first 2 he did, and then the 1 he did, and that's it. And so we can you know, write this down as 2 steps in the direction of the red arrow, and 1 step in the direction of the blue arrow. And I know most of you, or probably all of you, knows about coordinates and thinking coordinates, but these ideas appear much before that the idea of coordinate was in our mind. You know, it's really two directions and then how to combine them. And another thing is, well, I can do them in any order. I can go first 1 step in the blue direction and then 2 steps in the red direction. Of course, I have to do 2 red, 1 blue, and not, I cannot do 2 blue, 1 red. But anyway, so here it is. And well, clearly, if I allow any number, of course, I have to allow not only integer numbers, the monkey can arrive anywhere on the ground. If I now put the banana somewhere else, well, the monkey uses, in this case, 2 directions, but there's a new direction that appears, which is the green. I have to go up. And again, I can do the same little trick. And again, the order in which I do the steps is not important, but I need 3 directions. And of course, in my first choice, I chose these very particular directions, which are all perpendicular to each other. These are very special. That's not needed. It makes my life easier, and I can write things in a much more simple way. And I think it makes it easy for everybody to visualize it, but it's not really necessary. I mean, these directions would make it too. 3 directions that are not all in a plane would make it. Now, so if I allow the monkey to move in only 1 direction, well, he can go back and forth in a line, whatever the direction is, and he can't jump. Now, say that the monkey is moving on a circle. How many directions can the movie move along? And for some reason, this is not working, so I have to use my other, where is this? Gee, sorry. Okay. How many directions? Yeah, you're supposed to answer. And okay, I have answers. I want to see the answers. So I have many people sleeping. I can go a little faster. I am never sure of the audience, so I took this with peace and calm, and they said, oh, there is a chat, my chat helper. It's for me. Oh, no, it's you. Okay. Okay.
It's actually not letting me into the poll.
Oh.
Yeah,
oh,
I couldn't vote either. Sorry.
Okay, now it's working.
Yes. No, let me know. Yeah.
Oh,
Let me
got
know
it. Thank
this.
you.
Okay. Okay. So everybody, some people think 1 and some people think 2. Oh. None of the above. Well, the trick for thinking the answer is you go back to the image of the circle in your head and think, you're in a point and you want to go to another point. How many numbers you have to give the monkey? Can you do it with a single number? I mean, the monkey has already a direction of run around the circle. How many numbers do you need? So let me, maybe I should, no, not here, here. So if we look at the circle, sorry, okay, today I'm doing all the possible mistakes that I can do with technology. Here it is. Notice that if I have to tell the monkey to move, it really needs only 1 number to say how far it has to go. He has no freedom, even if, I mean, and I know some of you who answer, two directions is because the circle, yeah, lives in a plane. You cannot make a circle live naturally on a line, of course. But how many directions can it move? It's only 1 direction. It's 1 number that would allow the monkey to go from 1 place to the other. That's what that you have to keep in your head. Now, whoever didn't answer 1, you should ask. This is your moment to ask, because that's an important thing. In some sense, you can think about it locally, you know, around, if you're in a tiny, tiny piece of the circle, well, if you want to move forward or backward, that's the only thing you can do. You see, how can you move either a little bit forward or a little bit backward? And I'm still hoping for questions, so feel free to ask if you need. Oh no, so here we are. So again, you know, if you want to move if you want to move out of the plane, you need one more direction. What am I trying to do? I'm trying to define dimension. So I'm going to give you a possible definition. So we can say a space has dimension 1, and this is what I was trying to say with a circle. If when I have to go from one point to another, you know, I can go, if you tell me, I need only one number to indicate. So you have the direction and a number. Let's say that's dimension 1. It's a possible definition. By the way, this definition is really, I mean, it took mathematicians in a long, long time to arrive. It's delicate. I'm not going to give a completely correct definition even at the end of the talk, because it's hard. I'm going to give ideas. But again, there's some ideas that, you know, they live in the mind for centuries sometime, but having a rigorous definition takes a long time. Again, I can do the same definition of 2 dimensions in the same way. You know, I need 2 arrows, and you know, and the numbers that tells me how much in each arrow.
So somebody said in the chat, this reminds them of vectors from physics. I don't know if you want to elaborate on that similarity.
Yeah, right. No, the directions are vectors in physics. Yes. And then they call the possible linear combinations of a certain set of vectors. Yes. Now, Poincaré in 1905, you know, when people were still struggling, he gave this definition, which I think it takes a little hard to swallow, but it's really a good one. So he said, suppose you have a continuum. I mean, what is a continuum? It's a chunk of something, many points. And it should be, the continuum is as I wrote in the slide, it's a block. It comes all together. And you want to cut it. And you ask, how many elements? Suppose that I can cut it only with removing some finally many points. Then that's a thing of 1 dimension. So here is the example. I have the continuum, that's a little line. And if I remove 1 point, I get it in 2 pieces. And of course, you can say, okay, but if you give me a circle or an ellipse like I have here, if I remove 1 point, I'm not going to cut it into 2 pieces with 1 point. No, in this case, I need 2. And anything that we are going to call dimension 1 it will be something that if I remove finally many points, I can cut it into 2 pieces. And then maybe you guess, well, if I want to say what is something of dimension 2, something of dimension 2 will be something that to break it, I need to cut it with something of dimension 1. And how can I do this? Well, I already know what dimension 1 is. I just define it. So here it is. I broke this piece. So this should be dimension 2. And again, and so on. So that's a possible definition of dimension. You know, it's inductive. You define it by using the previous one. Does it have any problem, this definition?
Somebody just asked, how does Poincaré define what dimension 0 is?
It's a point, or a finally many set of points. Right, I should have said that because, you know, yeah, the point is unbreakable. So, I mean, if you think, I'm sure you'll get that if you get a space that is not nice, here I put nice spaces, you know, not very regular, you know, tame, you can think a little bit and get a not nice space that, you know, will make this definition fail. Still is a very good definition. It's just, you have to say which cases it doesn't work. Anybody see a case that it would make a problem?
Like the plane minus an axis?
What's that?
The plane minus an axis?
No, the plane is perfect. If I have the planar remove an axis, I break it into two pieces. No, a plane works. Good. I like people who, I always encourage people, you cannot learn without, being wrong and exploring. So more explorers. Anybody?
So are we questioning, like, where does Poincaré's definition for dimensions break down, in what cases?
Yeah, I mean, it's not going to face, there's a space that that is going to give something that is not what you want it to give.
Somebody suggested a space with greater than 3 dimensions.
Well, for 3, you have to break it with a 2. I mean, no, it's like for dimension n+1, you have to break it with a dimension n. That's the idea. But let me just tell you, I mean, I'm sure if you have enough time, you can do it. Imagine a double cone, okay? I have here in my hands, there are two hollow cones that they're joined by a point. So I can separate this by the point that joins them. If I remove that point, I get 2 pieces. But this has to be dimension 2, Well, Poincaré would have said, no, but this thing, this point is weird. Let's take spaces that don't have weird points. And, with spaces that are nice, that wouldn't happen. So anyway, the definition is a good one. And you could do the same for 4 dimensions, but we can't see it. So we're going to work a little bit on trying to see 4 dimensions. And I mean, the idea of 4 dimensions, I mean, I've been reading a lot for this talk. It's really fascinating because it's very similar to the idea of infinity in mathematics. When people thought about infinity in mathematics, they had a lot of objections, and they often were not because of mathematics, because when you say infinity, it mixes with religion and other things. Well, 4 dimensions will ring, people, what would be the objection of defining 4 dimensions? Anybody can imagine? I'm opening the chat and see if it. Why, I mean, when do you think the idea of 4 dimensions appear in math? I should have put that question next time I give this talk, if I ever do. Well, risk it in the chat, invent something, come on, be wild. Don't Google, think. In a matrix, and when the idea of 4 dimensions appeared, when, which year? Invent a century.
1905.
The 19th century.
1905, huh?
The 19th century.
Sorry, I couldn't hear.
The 19th century.
19th century. What else? Why not before? 20th century, I have here the 0th century, okay. Einstein professor. So, well, 18th century, it appeared in the 19th century, but why it took so long? Well, because, have you ever seen a space of 4 dimensions? No, I think. Well, the problem is that people had mathematics as a mirror of reality. I mean, geometry was true. Like Euclid had axioms, and axioms were true things that are obviously true. And Euclid was uncontested. I mean, the trueness of these axioms was uncontested until quite late, when, well, they started to work in this fifth postulate, and people started to say, well, it's not as true or not. We can assume these things and arrive to some conclusions. We can assume other things and arrive to other conclusions. And the issue is that I should assume things that are good in the sense that they are consistent, that they don't lead to contradiction. They have to be also meaningful. But the freedom of saying I can assume almost whatever reasonable, took a long time to arrive. And here what I have is, in our heads, we can construct spaces that maybe, we don't see. So here I have a Pac-Man that is student-made, Ajit Gary, and this Pac-Man is working on a cylinder, kind of. You see that, the little monsters, they go out in one side and then come in the other side. And when you play the computer game, you automatically see that, here is moving together. You automatically see that you make the cylinder in your head. I mean, you see it in a flat screen, but you know that it's a cylinder, and that's a cylinder. Even if you see it flat, something that works like a cylinder is a cylinder. So this is an example of a space that exists in mathematics we can construct in our heads, but maybe it's not a way to see what you get. So we are going to try to do the same thing with 4 dimensions. Okay. Question: how many dimensions the hollow cylinder? And I have to, here it is. Oops, yes, good. This is anonymous, so you can, answer whatever without risk of nothing. Nobody should have risk. This should be a place when people ask and it's free. So the idea again, well, most of you are answering 2, and that's right, because again, we need 2 dimensions, you need 2 directions, 2 arrows to arrive, 2 numbers to arrive from a place to another with a direction. You can think, always the dimension is something that is local, in the sense that what only matters what happened in a real point around you. So the hollow cylinder, again, like the circle, well, the hollow cylinder lives in the 3 space, but the dimension is 2. Again, how can I separate the hollow cylinder into pieces? Well, with a curve, I can break it into pieces. So I need a space of 1 dimension to break the hollow cylinder into pieces. This is a nice space, like, the ones that, follow this Poincaré definition. So it satisfies that definition. Oops, nope. Okay, so now, and again, I'm going to the wrong one. Okay, so now we're going to, so what is a square? I like definitions of a square. Now it's activated. You shouldn't be able to see it. I want people to answer without feeling constrained about other people answer. Don't Google, because then it's boring. And maybe you don't have how to answer. It should be activated. Well, I'm going to put it in the other one. No, square, the geometric figure, I mean. Okay, and now, okay, we have a quadrilateral with congruent sides, okay? An equilateral, quadrilateral. So a parallelogram is a square because it has congruent sides. A square, closed 4-figure, each side is equal length and right angled corners, okay? So it's a really good exercise to really try to define something. I said with precision what it means. Okay, and now we have votes. People are voting. So I said it geometric, so hey, no hey. Lost my sense of humor here. So quadrilateral with equal size is not. Let's vote that down, because again, a parallelogram, if you have a square and you slant it, it still is going to have 4 equal sides, but it's not a square. Okay, so I'll choose, well, you can say a square is a rectangle with all the sides of the same length. That works. A figure in the 2D plane format 2 pairs of congruent parallel lines joined together. That's again a parallelogram. So 4 congruent edges and interior angles, although there's no verb in that sentence, so I don't know exactly. It's a figure bounded by 4 congruent edges and 4 congruent angles. And they have to be 180. So that's a square. So why are squares interesting? Why am I talking about squares? Well, this is one of the things that mathematicians are fascinating. patterns. We like things that have repeat in some way. So 4 equal sides and 4 equal angles, make our math hearts happy, like this, the symmetry. One way to see the symmetry is that if I grab the square and I rotate it around the center, say 90 degrees, and I put it back, well, if you were not looking, you wouldn't know that I moved it. That's a symmetry. Well, the square has a lot of symmetries. I can reflect it in the middle or reflect it across diagonal. That's an enormous amount of symmetries. So that makes it mathematically beautiful. Patterns, repetitions. And like the square, we have the regular pentagon and the hexagon and the octagon and so on. So all these shapes, mathematicians have known them for, thousands of years and studied them and repeated them on and on. And these are regular polygons. And this expresses the idea of, we are generalizing, like I abstract this, when you define a square, which is maybe the best that you think, the first, of course, is a triangle, the equilateral triangle, but then we say, okay, what is it? It's a shape that has has all these sides congruent and all angles congruence, and then I get the regular polygons. And one has to be a little careful with the definition, because in this case, for instance, I have shapes that have all congruent sides, but not congruent angles. So, one has to, when make definitions, be precise. So here I generalize, and this talk I gave a version of this talk in Spanish. So I have a word in Spanish, generalizar, which I can say very well, unlike the English. So a segment it generalizes a square. That's one way, one more dimension. A segment is like a square in dimension 1. And then I can generalize adding size. So I can add dimensions or add size, and I'm generalizing my idea. And so I can keep going with this generalization. And then, we have the segment in dimension 1, the square in dimension 2, and a cube in dimension 3. And again, I can go to the right in my generalization. And now how can I generalize the idea of regular polygons? Well, regular polygons were shapes, in some sense, were shapes bounded by segments which had the most amount of symmetry in some sense. You can say all sides are congruent, all angular congruence. Now, when I go to the Platonic solids, how can I define them? I don't think I have a question for that. Let me see. Yeah, let's see. What do the Platonic solids have in common? Let's find something common about the Platonic solids. Maybe I should show you. I mean, I'm very small here, I know. So here I have, well, the cube is a Platonic solid. The tetrahedron is another Platonic solid, the first one that appeared there. It's made of equilateral triangles. The dodecahedron is another Platonic solid. So what do they have in common? Oh, I'm not activating. Sorry, you should yell at me when I don't. It's hard to do math. And here I have another Platonic solid bounded by 20 triangles. And here I have another one bounded by 8 triangles. So what do they have in common? Same three-dimensional angles. Yeah, they have the vertex. Yes, very good. They're all rigid. Yes. But everything is almost rigid. All equal sides. So what are the sides? Now, when you say a side here, what do you mean? Here I have two. Well, a side here, what is the side of this? Each face of a Platonic solid is a regular polygon. Okay, good. Each face is a regular polygon, and all faces are the same. Yes. All faces are the same regular polygons. So all faces are the same regular polygons. Is that enough? No. I also have to require that at each vertex, I have to have the same amount of regular polygons. I need to have 3. Otherwise, I can make weird things. And good. So now I'm going to skip this question. Let me see where am I in time. Oh my, I need time. So somebody said that the Platonic solids, the elements of Euclid were written to explain the Platonic solids. Then apparently that's not true, although it's a lovely idea, but it's not true. But it is true that the books of Euclid, which, by the way, if you never read, you should look at them at least a little bit, because it's a marvelous piece of math, and there's a very nice version online. If you want to ask me, send me an email and I'll send you there. It's really amazing, you know, and it's worth to go and spend some time there. It's so attractive that, as you see in the lower left, there is a fragment of Euclid. That's the oldest fragment that we have. It was written in Egyptian papyrus. And, you know, we had, as you know, before the printing, there's many manuscript versions, no original arrived to us. And it ends with the construction of the Platonic solids, explains how to construct. I mean, if you can construct it, they exist. And so, okay, so now let's move dimensions. So there's a book called Flatland that appeared, I think, in the 1880 or so. And it's a story of a square that lives in a world that is flat. You know, the houses are pentagonals, and the more faces you know, the beings there, they are regular polygons. The more faces, the more size they have, the better off they are. Women are segments because they are the worst. It's a satire of this society, the Victorian society at that time. And so now, how would it look, the world, you know, the two-dimensional world? So let's try to imagine. So for that, imagine that this is a two-dimensional world. I have this tiny seal, the black seal on the lower right, and she's looking at the three beings. We have to put a little thickness, but, you know, it's super tiny thickness. And then we like to see what is the view. How does the world look like to an inhabitant? By the way, you know, whoever you who like geometry, a wonderful geometer who died a few years ago, Thurston, he said, sometimes it's good to think yourself inside the space. So here we're thinking ourselves inside a two-dimensional space. And here it is. So the eye level is that, you know, marked by that arrow. And this is what the seal would see, you know, just would see some segments of different thickness, sometimes not relating to the actual size of the shape. So this is the look, the landscape on this two-dimensional world. And so suppose that this two-dimensional being wants to understand a cube. So he has his mind, you know, has a mind that can think. So what can he do? Well, there's one way. Let's see if I can point with my pencil here. Oh, yeah, here it is. Okay. So one way is going back to this idea that we're generalizing the square. So here we have a point, and then we're going to start with a point and move, separate, you know, make 2 points and separate. That makes you a segment. Then you have a segment here, and you're going to start with your segment. This is your segment, and you're going to kind of imagine that you double your segment and you slide one of the segment down. Sorry, you have a segment double and slide them down. And then again, I have a square, double it and slide it away. So that's one way of constructing, you know, all the cubes. And this is one way that this two-dimensional being can start thinking, because he can imagine going from the point to the segment, and can imagine going to the segment to the square. And then he can say, well, as I was going to the segment to the square, I can go from the, oops, I didn't want to, what, sorry, nope. Let me move. Okay, here it is. This movie is revealing, no, come on, oh, here it is. So this is the construction I was trying to describe. So you go from one to the next to the next. and you make, yeah, this is a square. So the two-dimensional being has to imagine the last piece. But, since you did all the, this is a lot of things, when we ask you, give you the first term of the sequence and you say, do the next, well, this is again, a game of imagination for that. Another way is, I call it Lego in my summary, is like here, let's break a cube, again, it says cubo in Spanish. And well, the two-dimensional being can look at the pieces and how they glue to each other. It cannot actually glue, so the folding that we are doing, this is when we're using an extra dimension. When you look at the flat piece, this is called a net, there's many ways to break it up and make a net. The flat piece, well, it has only the indication of how to glue. Another way of thinking is projection. Again, we're trying to teach this two-dimensional being to understand a cube. So by projection is looking at the shadows of the thing. And there's many ways of doing it. Either you have one lamp like here, in a point, that's a certain kind of projection, or imagine that you have a light very, very far away that makes all these rays parallel to each other. In this case, they are perpendicular to the plane, or they can be not perpendicular, but all the rays go. And then, you always, when you do a shadow, you always distort your shape. It's not exactly what it is, but it gives you an idea. It's like you look at your shadow on the floor, well, that's not you, but it can give you an idea of you in some sense, but you have to know exactly how is the light coming and, certain things to reconstruct your image from the shadow. Another way of thinking, and here we're going to show our being a sphere, is now look at slices. So our being lives here in this yellowish plane. So now we're going to, sorry, oops. Okay, sorry, I was prepared to do this in the computer, and okay, come on, oh, here it is. So this is, what we see below is what the being sees. But, we are three-dimensional, we see the whole thing. The two-dimensional being sees only slices. And here are different slices now of a square. And again, this depends on how you are, project how you're slicing it, in which direction enters the plane. Yeah, there's another way. And here there's a third way. And it's the same shape.
So there's a question. Somebody asked, is that why in graph theory, they have certain graphs that are isomorphic to other graphs? You can project them to a 3D object and see if those are isomorphic as well.
No idea. I don't know about anything about graph theory, so I cannot really answer that. But it could be. So, and here we see another movie of a cube, passing through the plane, and we see both the shadow in this case and the section. So now we're going to try to move one up. So now we are the limited one. We live in 3 dimensions, but imagine we could perceive 4. So here we saw this. This is what we would see if a 4-dimension is a 3-dimensional sphere. 3-dimensional sphere, it's always confusing, but the 2-dimensional sphere is 2-dimensional, okay? 2-dimensional in the sense that we've been discussing. It's a hollow sphere. And so here is a 3-dimensional sphere passing through our world. What we would see is a bigger and bigger and bigger 2-dimensional sphere, and the analogy is what you're seeing on the left. So we are observing the same as the being in flatland observed, the same type of phenomenon. But he sees a segment getting bigger and bigger and bigger. We see a sphere going bigger, 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 and then smaller, smaller, smaller. Any question? Now, here is the net. And of course, now if you want to do the net is all the pieces and you glue them together. Well, I can't. In the same way that, to glue the box, the square, we have to fold it outside, you have to go outside the two-dimensional plane. If I have a box, so here is this thing I have here. I don't know, let me just put it bigger. So I have, these are 8 cubes. And well, this is a net of, and I have, give me 1 second. What is it?
Oh,
This is a net, here it is. This is the net of a square. Now, if I live in a two-dimensional world, I can't, and so I can't fold here. I can't do this and this to glue it. I can't fold because I'm constrained to the plane. We live in a three-dimensional world. We can't fold this. I have one more dimension. Maybe in Harvard, they have one more dimension. Stony Brook, we don't, because we're a public university. But if I have one more, I could fold this and this cubes. So this and this, these two squares get glued. In the same way that I have segment, and I fold them, coming out of one dimension. Sorry, let me just show it here. I fold them so they glue. In the same way I could, but I need to get out of, the 2 dimensions here. If I can't get out of the 3 dimensions, I could fold this and make a cube. Now, many of you probably seen an image of the tesseract that looks like this, or the 4-dimensional cube. And in some sense, well, maybe I'll go in a second here. This is and is not a cube, a 4-dimensional cube. Why is not? Well, because we're talking about figures that are regular. This should be made of cubes. Now, if you look at this shape here, let me see if I have it. I should have. Let me show it here. So this shape here is going to appear now. It's not made of cubes. I mean, there's a little cube here in the center, but the other things are, are polyhedra that have, faces, but it's not made of cubes. They are deformed cubes. So to put this thing, to put a 4-dimensional cube in a 3 space, we have to deform it in some way. You try to deform it as nice as we can, but we have to deform it. This is a shadow. And in fact, it's missing one side.
So somebody asked, going back a little bit, did you mean that we see a circle when a 4D sphere passes through our 3 dimensions?
Say it again.
Somebody asked if you meant that we see a circle when a 4D sphere passes through our dimensions.
Wait, let me read. I think, which one you said? Oh, do you mean that we see a circle when a 4D? Yes. No. So let's go. Let me go back. Yeah. So when we see this, so what we see when a three-dimensional sphere is something that we cannot visualize in a 3-dimensional world. In the same sense, like a 2-dimensional sphere is the green thing that it doesn't live in a 2-dimensional plane, because the 2-dimensional plane is flat and the 3-dimensional sphere cannot be made flat without deforming. So a 2-dimensional sphere is like a hollow ball. That sometimes the 2 and 3 make people confused. A 3-dimensional sphere is something that we cannot represent in a 3-dimensional world. So when a 3-dimensional sphere, which lives in a 4-dimensional world, in the same way that a 2-dimensional sphere lives in a 3-dimensional world, okay? So here we have, again, a 3-dimensional sphere, sorry, a 2-dimensional sphere, which lives in this 3-dimensional world and is passing through a 2-dimensional world. And here, and the red thing represents a 3-dimensional sphere, which is a being of a 4-dimensional world passing through our world. So this is what we would see. Hopefully I answered that. I think I messed up when I was talking.
Somebody else asked, what about a hollow cylinder? It's two-dimensional, but we can't visualize it unless it's in three dimensions, right?
Exactly. That's the same. Well, I mean, we can visualize it, but the person in a flat land, a person who lives in a flat world could not have a cylinder in the flat world, even if it's two-dimensional. Yes, that's exactly, yes. Like a circle is 1D, yeah, now all the chats are good. I mean, a circle is 1D and a sphere is 2D, because this is the really intuitive definition. Is not, the dimension is not in which dimension you live, is, you know, the dimension is something that is inherent to the world that the space itself. It's not where you live. Okay. So these are good things that happen. So it turns out that this green circle wants to go and play with his friends or her friends or their friends, but it cannot cross the black line, and it can, you know, so this green disc is really sad. That's a tear, is crying. So how can it go without crossing the black line? How can it go and oops, time is fast. Just answer me in the chat, that will be faster. Any idea how can he visit his friend? How can the green circle go and visit their friends without touching the black line? Jump. Yes. He can jump. But of course, you know, being a two-dimensional being, well, I'm playing with the rules and I'm not give you very clear rules. Limbo, I don't know what that means. Teleport, yes, that's true, but, you know, it's mathematically not challenging for me. Yes, so, you know, he visits his friends by getting out one direction. So this is the way he does it. I mean, and for him, it would have been inconceivable to go and visit unless he has a way of getting out of his world. Again, you have to live in two dimensions to grasp it. Imagine yourself in two dimensions and you will see, because that will help you to imagine the four dimensions being in three. So now he's happy. And this is a very interesting question. Can we make these triangles coincide? Well, again, you know, without leaving the table, you can't. These are two triangles that, from the point of view of Euclidean geometry, they are congruent. You know, they have, you know, the whatever congruence of triangle you want to use, you will make them congruent. There are three congruent sides, three congruent angles, but there's no way to slide them to make them coincide one or the other.
I think referring to the last example, somebody asked, wait, so to meet his friends, he has to leave his dimension.
Yes. Yes, 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 thank you. Yes. And again, this triangle, to make it coincide, we have to take it out of its dimension. The table is the flat world where the triangles live. You have to twist and then put them back. And then, yes, you can mislide them and make it, you know, congruent. And so here is a little piece, you know, but, you know, I want to convince you that really dimensions are very useful. So that this very nice movie called The Time Machine is based on a novel that was published in 1895. It was this novel called The Time Machine, those H.G. Wells, was incredibly popular. And, you know, it starts this, let me just see if you can see it.
Up, down, forwards, backwards, sideways. When it comes to time, prisoners.
Taylor's breakthrough into the realm of the fourth dimension is defied by his friend Alan Young.
That machine can do what you see it can. Right, George, before it destroys you.
Every moment is a year. Through the atomic wars of the future on an incredible excursion into the unknown.
Anyway, so this is, by the way, this is the, let's see if I can make this bigger. No, I can't. But this little machine here this is the artifact that he used. He constructed a machine that will travel in time. And the novel starts saying that, well, there's 4 dimensions. The 4th dimension is time, as many of you said in the beginning. And well, if you can travel in space, you can travel in time, why not? And he travels and, goes around the world. But that tells you, like in 1895, this idea was already, I wouldn't say popular, but, accepted by a big chunk of people, the idea of 4 dimensions. Still, to think of 4 dimensions, they have to think of time. Oops, sorry, that's enough. So here is another use of 4 dimensions. So again, now we are in a city. This is the cartoon of a woman, but imagine that these are 2 real women. One has the heart on the left side like everybody else, and the other one has the heart on the right-hand side. Can we make them coincide, one with the other? This problem is identical to the problem of the triangle, the 2 triangles on the green table, but with 1 dimension more. So you have 2 3-dimensional beings living in a 3-dimensional world, and they are congruent, they are equal, but I cannot make them equal. They are the mirror image one of the other. So how can I make them equal? Well, we give them a key, and she can go to the 4 dimensions, not the 4 dimensions. She just travels in the, in this 4-dimensional world that we can only perceive 1 slice, and then comes back. And since she flipped, there's a way to do it, and you flipped, and then now the heart is on the other side. So this is in the 4-dimensional world. Another very useful feature of this, oops, sorry, clumsy person again. Another useful feature.
Oh, sorry. Somebody said, can you flip a left glove into a right glove?
You can, in the same way, yes. If you can go out 1 dimension. Interestingly enough, with gloves, you can also put the glove inside out, and that would make the trick. Although you shouldn't flip your hand inside out, because that can be painful. But the glove, since it's 2-dimensional glove, you can do it in the 3 dimensions. It's the hand is not 2-dimensional, yes. So flipping is basically leaving the 3 dimension. Well, in order to flip, think of the triangles. So the question here is, flipping is basically leaving the 3rd dimension. In order to, if you have a thing and the mirror image of a thing, in order to make them coincide, you need 1 more dimension than whatever you're leaving. If you have 2 dimensions, you need 3. If you have 1 dimension, you need 2, and so on. To flip things, to make a thing coincide with this, if you have 2 things that are equal, except that one is the mirror image of the other, that is we need 1 more dimension. So here is 1 more use of 4 dimensions, which is that, well, again, if you look at this, the little square, and he's in a jail. Well, we can go and save him, we just go and grab him, if he come from our 3-dimensional world, we can grab the square and remove him out of the locked jail. But in his world, the square is locked. It's in a jail without a door, no way out. In the same way, a 4-dimensional being, if we have 4 dimensions, it can, take this woman out of the box without even breaking the box, which has no door. And this, again, the way to digest this idea is, I'm sure you can see this one. Well, think it's analogous to the one of 3 and 4D. And I have 9 minutes. So remember that we discussed we talked about the Platonic solids, and I wanted to go a little faster, but so the Platonic solids, well, we had the regular polygons, Then in 3D, we have the Platonic solids. And in 4D, we have the analogues, which are called 4D regular polytopes, and there are 5D regular polytopes, and so on. Now this, of course, the things I'm showing you again, well, it's kind of weird because these are things that are 4-dimensional that I'm making look 3-dimensional, but then I'm showing to you in a screen that is 2-dimensional. But the picture, the perspective makes you visualize the idea that these things look 3-dimensional. They are 4-dimensional. Again, I'm just looking at shadows, or, you know, in fact, I'm only looking at edges and vertices. And these were discovered by Schläfli, who was a mathematician. He apparently did all his work, an enormous amount of work. It was very long, not very nice in pictures, and he sent it in 1853 to a few places. Nobody accepted his work. He did fantastic things in complex analysis and other areas, but all his discoveries, which were very, very advanced, you know, I mean, we were not ready for him, were published after his death. In, you know, now it's famous. Many people discovered the regular polytopes independently. But anyway, so here we have now generalizing one more step. So there's the cube, you know, exists in all dimensions, you know, from a point to a segment to a square to a cube, all dimensions. And the polytopes also exist in all dimensions, although the number, well, maybe I'm not talking about how many are they. There are 6. Oh, sorry, I'm going. I want to finish with just one more little thing. Maybe let me talk about Alicia Boole, who's, if you know me, you know how fanatic I am of her. So Alicia Boole was a young Victorian lady who at some point in her life, when she was about 17, somebody came to her house. It was a friend of the family who was quite interested in visualizing, you know, 4-dimensional space. And he has a puzzle. This is a piece of the puzzle here. These are these cubes, but they were like, I don't know, more than 100 cubes of different colors with complicated names and very complicated and cumbersome procedure to visualize the 4 dimensions. She was quite interested in that and kept thinking and thinking. This is all her family. She's the daughter, by the way, of George Boole, who's, you know, for the Boolean algebras and Boolean searches that you know in Google or in many places. He is another out of the charts character. And this you know, remarkable story. Alicia Boole Stott, she rediscovered this equivalent to the, you know, the Platonic solids in 4 dimensions. And it was just, she lived by herself and was thinking about math and made the models of slices. And I'll show you the movie of the slices. But for some reason, at some point, a magazine, a publication, a mathematical publication from a Dutch mathematician landed into her hands. And this picture was in this publication. It was drawn by this guy who's a Dutch mathematician, Peter Schoute. And this model, Alicia made it before looking at that picture. So these two people, one in the Netherlands, the other in England, made identical figures more or less at the same time, representing the same thing. And she contacted him, and he was quite amazed that this Victorian housewife has all this knowledge, and they wrote papers, and yeah, they were the same thing. And these are ideas that Alicia did. She called this procedure contraction and expansion. It was how to transform, you know, one regular polyhedron into others. So here we're going to the icosahedron, the one with 20 triangular sides, to the dodecahedron. This is another one. It's the octahedron to the cube. Again, she systematized this procedure. And the fantastic thing is that she could see all inside her mind while she was, you know, taking care of the children and, you know, having a life, not a lot of money. So when you don't have a lot of money, you have a lot of little things to do for work. And I'll finish with this. So she studied, you know, there's one space called the 120 cell. What is the 120 cells? So what you see here, this is the net. There are 120 of these dodecahedrons that I have to glue in a certain way and then fold, but you need one more dimension to fold. And so this is one way to think about it. I start with one, this is a dodecahedron, a single one. And it has 12, let me show you here, I'm showing you with my hands. It has 12 pentagons, regular pentagons at its faces. So at each of these 12 pentagons, I'm going to glue one pentagon. Very good question. One is 120. I'll answer in a second. So I'm going to glue here 12 of this. And then I'm going to fold them a little bit, and then here is where I don't have enough dimensions. And then I'm going, so this is the second layer. I glue 12. And I'm going to have a third layer, which are 20. I'm going to glue 20 dodecahedron around there. And then I'm going to do 12 again. And then I'm going to do 30 again. So I imagine that I'm putting layers and make it bigger. And I keep going. And at the end, after I'm gluing and gluing, I'm going to end up with a dodecahedron, big dodecahedron. And then I'm going to glue a dodecahedron, and I can't explain it. But imagine that, let's do it like this. I have two discs, my two hands are two discs. And I'm going to glue them like this. I make it to sphere. So I started with two things that are, two-dimensional with a boundary, and I glue them, and I get another two things which is two-dimensional and has no boundary. Well, now, if I have two dodecahedrons, it's hard, but these are like two balls, and I glue them through the boundary, and I need one more dimension to do it. What I get is the 120 cell. And the question of 120 is, I could answer, well, why does a cube has 6 sides? Why? Well, I'm not going to do a proof, but if you want to do a Platonic solid that faces are squares, think why. Well, I can only put 3 at a vertex. I cannot put 2, and think why I cannot put 4 because it will be flat. So I put 3, and if I put 3, when I start building, I start with this, the bottom square, and then I put 4 squares around, and then the only choice I have is to just glue it, another square on the top, and close it. So that they have to be 6. If I made it with square, they have to be 6. The same argument, or very similar argument, you can make, but now you get 120. And so Alicia, I made this little movie where I think she could see this in her head. She drew the pictures downstairs, and upstairs, these are all these layers of the dodecahedrons and a 3-plane moving around. And, and every time you slice a different layer, it's a different color. So these are the things that, she could, she worked really hard, I think, but finally she managed to see that all in her head. And maybe this is a good time to finish. And anyway, sorry, any question? I should have stopped for questions before.
There was a chat I didn't see a minute or two ago. Somebody said, why is it 120?
Yeah, that I kind of answered. I hope to answer is, it's the reason the 120 is the same way that, you have 6 squares making a cube. When you start gluing the dodecahedrons, at some point you're going to have 119, and you have to put the top, that is the last dodecahedron. In the same way that if you build square by square a cube.
Professor, I have a question.
Yes.
I guess like in regards to, like for example, if we were to have 2 5D shapes, how would we say if those shapes have similar properties? How are they isomorphic? Like, could we only do that mathematically, or is there a way to visualize that?
Well, there's an mathematically, and visualizing for me is the same. I am a visualizer mathematician, but it's the same idea as before. You start to construct, I don't know exactly what you're asking, but you can have, shapes in 5D, which are the mirror image one of the other. And the thing is, the property of these shapes is that if you look at the relative distance between pairs of points in the shape, they are the same, but they're mirror, I mean, like a person or, like a mirror image, the distances are the same, but you cannot make them coincide. And you cannot make them coincide if you are constrained by the number of dimensions of your space. Of course, the things need to be 5D to not be able, because if you have a 4D thing living in 5D, then you can flip it. You need space to flip. Any other question? I'll let everybody mute.
Hi, Professor.
Hi, nice to see you.
Nice to see you too. I have a question.
Okay.
Well, kind of, sort of question, but have you ever seen the movie Interstellar?
No?
Oh, because like it's basically like a space travel movie, but there's this one scene where he's like in the 5th dimension or something, and he sees like his daughter in the past, and he's trying to like get her attention, but it's like, so she thought like in the beginning of the movie when she was young, like she thought there was a ghost in her room because like stuff kept like falling on the floor and stuff, but it was really him like in space in the future, like trying to get her attention. It was crazy.
Yeah, no, science fiction used a lot these ideas, and quite early. I mean, Wells, as I said, these ideas, I mean, I forgot to mention that, the first person who thought about the flipping, like how can you flip something in 3D, and make it coincide with some mirror image, was Möbius, our guy from the Möbius band. In 1827, people were writing against a 4D because it was like, oh, how can you do it? If you cannot, there was emotional responses. This is contrary to nature. Why are we thinking about this? This is the only thing that exists. And Möbius, he said, oh, maybe you can flip, if you have 4 dimensions, you can flip in the same. He was arguing by analogy, 2 to 3, 3 to 4. And, but it took, because when all these non-Euclidean geometries came and people started to see that, geometry doesn't have to be a mirror of reality, then, we had mathematics that became more abstract and less true, whatever that means.
And that reminds me of, how people were hesitant to adapt the notion of complex numbers.
Yes. Yes. The complex number and infinity. I mean, poor Cantor was really miserable, because how can you talk about infinity? How can you say there's 2 infinities different than the other? I mean, he just wrote nice, rigorous proofs, but, mathematics, we praise ourselves to be not so emotional, but we're not always achieving that. And I wonder, I always wonder, well, right now, we are very happy with our mathematics, but I wonder what things are we thinking about that in 1,000 years they're going to think, oh, remember these people in 2020? So silly, what they believed. I see a chat. Now I see a chat, but I lost it. Where are the chats? Here. This just makes, math, there's a lot, I mean, there's a lot of math, math is very good for fantasy.
Okay, so thank you so much, Moira, for this talk. It was a really great experience. So